The idea of a limit is simply what is happening around that value. And as you're moving closer and closer to that value, what is your function doing? And I think that's the whole idea of a limit. And when it comes to derivatives, it's simply about taking that rate of change, right? And when that rate of change, equals it's divided by 0, then what do? That's exactly where limit comes into play, right? So limits have a lot of roles in calculus, and it's kind of also where a lot of it was defined from.
And for to describe a limit formally, there's something called an Epsilon Delta proof, which we are absolutely not going to describe right now.
I mean, we can give a general idea, though. I think we can give a general idea.
Yeah, we can give a general idea, but there's no way that we're going to convey the full picture of what's actually going down.
The very, very general idea of an Epsilon Delta proof, is basically let's say you have a function like y equals x squared, right? Or any kind of function like that. Just not getting into the math, just the theory, just the idea behind an Epsilon Delta is basically, let's say you want to find your value of your function, let's say at x equals 5. Right? Now, obviously, you already know what it is. It's 25 because it's x squared. But let's say you don't know the value. So the entire point of the epsilon delta is if, let's say, you have x equals 5, the idea of, once again, this limit definition is as you get closer and closer to x equals 5, your function gets closer and closer to y equals 25. And that's basically the epsilon delta. So let's say you take one interval away. So your x equals 6 and x equals 4, right? Then what does your function equal? Your function would be 16 and 36. And as you get closer and closer to x equals 5, the idea is simply your function value is getting closer and closer to 25. So what that proves, what the epsilon delta can help you prove is, let's say you're trying to prove why the limit as x approaches 5 of x squared equals 25. Let's say you're trying to prove that. Now, if you're trying to prove that, that is where you would use this epsilon delta. That I can find some value close enough to x such that all values of your y are very close to 25. Right?
And basically, another idea that ties into that is that calculus is all about zooming in.
Yeah.
Right?
Yeah.
The idea of zooming in infinitely kind of also ties into continuity. But what I was trying to say is that you have a point, and usually when you're taking or trying to prove a limit, it's going to be some kind of function that has a discontinuity at a point.
Yeah.
And usually when you would draw that on a graph, you would draw a hole, right? But what you need to understand is that hole is just one point, which means that you can zoom in as close as you want to that hole, and there will always be values to the right and to the left. And so to prove that the limit exists, or the value, what am I trying to say here?
The limit
the function
equals a number,
converges to that one point.
Discontinuous,
right?
Yeah.
What you're actually trying to do is you're basically zooming in very close, and you're saying, well, the closer and closer you zoom in, the closer and closer the values actually reach that point. But you have to be careful, because when you're taking a limit, it doesn't, the function doesn't actually have to be defined at that point.
It's true.
It just has to be defined very, very infinitely close to that point. And that's kind of the most fundamental idea in calculus, I believe.